going to change topics a bit, but interesting, some of the modeling that I'm going to use here is exactly the same. And I'm going to talk about the urban or constructed environments, maybe in a way that you haven't envisioned them. So let's talk about the urban water cycle, because frankly it is the urban water cycle that drives all of the pollutant loads that we are trying to manage within the built environment. So during wet weather events, we have constructed an environment that is largely paved. As a result, we have completely changed the relationship between rainfall and runoff. And so what I want to focus on is the surface precipitation over a 10-year period and compare that to the pre-development condition, 252 inches of surface runoff as compared to 54 inches of surface runoff. And what I'm here to tell you is till we solve this problem, we are never going to solve our wet weather pollutant load problems. It's simply not sustainable what we are doing in this country or in any country. So let's look at impervious areas, and I'm going to use the example of the state of Florida where I live. Here's the University of Florida here. Here's Jacksonville, Tallahassee, Orlando, Tampa, Miami. So as you look, as you go from green all the way to black, you have higher imperviousness. Higher imperviousness means more runoff, but it also means more degradation in terms of water chemistry. If you look at this a little more closely, we're looking at the Orlando area. You can see that the urban core is absolutely dominated by high impervious areas and high water pollutant loads. And in fact, most of this is generated by motor vehicles that you and I drive every day. So, how large is the problem? Let me compare it to something we're all familiar with. We've all been trained on the wastewater side, but maybe not so much familiar with the urban stormwater side. So this particular city that I'm looking at is a Midwestern city in the USA, population of 800,000, mean annual rainfall of roughly 1,000 millimeters, and the area that I'm comparing is 40 square kilometers of pavement. That pavement represents about 15% of this Midwestern city. So if I compare annual runoff, stormwater, to wastewater, the annual flows are quite similar. Chemical oxygen demand, quite similar. Total suspended solids, those solids that remain suspended in an Imhoff cone for 60 minutes, actually quite similar. Now, that excludes settleable solids and sediment, which would actually make the total solids number closer to 600. Total zinc, copper, lead, and cadmium, total being the sum of the dissolved in the particulate fractions, however, in annual runoff is much, much higher than what we see in domestic wastewater. We wouldn't think of ever discharging wastewater untreated, and yet we do so with runoff every single day. The magnitude of the problem is actually greater than wastewater treatment. So, in urban areas, the primary vehicle, the primary source and sink for chemicals is particles. Particles that you and I generate primarily through the interaction of our motor vehicles with pavement. If we can learn to manage and control particulate matter in the urban environment, we can go a long way in managing pollutant loads both onto and from that particulate matter. Now, particulate matter is not just particulate matter. It is not just measuring this thing called total suspended solids. Particulate matter represents a whole spectrum of size distributions, from dry deposition at the upper end of the urban watershed, and as we move down the watershed, obviously this becomes finer and finer as different particles are selected and removed within the urban watershed. This may look complex, but if you apply a cumulative gamma function to these data, you can simply model all of these data by a scaling parameter and a shape parameter. So now 2 parameters, and you can rebuild all of this data. Now, the common perception is it is the finer fraction of particles that contain most of the pollutant mass. This is incorrect. It is the mid-sized coarser fractions that contain most of the pollutant mass. Why? The reason is simple. Because the total surface area, not the specific surface area, the total surface area associated with these mid-range particles to coarse particles is the highest. There is more surface to put chemicals onto. If you look at the surface of urban particles, they both are geochemically conducive to adsorption and desorption, plus they have very high surface areas if you look at actual real particles. Physical indices for these particles, the D50 of the clay size fraction is about 3.5 microns, a density of about 2.68, a specific surface of 130 meters squared per gram, a point of zero charge indicating at the pH of 5.8, and the D2 fractal dimension about 1.93. So again, these all indicate that these particles can be relatively reactive particles for adsorption as well as desorption. If we are able to track, to model, to measure the fate of particulate matter, and we know the association of chemicals as a function of the size of that particulate matter, then in fact we know the fate of those chemicals also. In addition, for microorganisms in the urban environment, particles are home sweet home to these microorganisms. So in fact, control of particulate matter in the urban environment also means control of microorganisms in the urban environment. And in addition, really not the focus of this talk, but those of you who might go out and sample and analyze, trying to characterize urban stormwater, recognize that urban stormwater is not wastewater from a characterization or from a sampling point of view. Very dynamic partitioning occurs for all of the different chemicals at different rates. So how you sample and how you analyze is absolutely critical to your results. Now, I want to talk about computational fluid dynamics. Typically, in an analysis process, we can look at ideal overflow rate models without a particle size distribution, ideal overflow rate models with a particle size distribution, semi-empirical models with particle size distributions, but most of the work we do is with multi-phase computational fluid dynamics to look at the fate of pollutants and particulate matter. So what is computational fluid dynamics? By the way, this is a real picture from southern Italy. Basically, all we're doing is solving the continuity and momentum equations, part of the classical Navier-Stokes equations. We're doing this. What's unique for what we're doing is we're doing this in two phases. Classically, this is done with the continuous phase, say, for example, in a Eulerian frame of reference using a K-epsilon turbulence model. We are coupling that in addition with a particle size distribution for the particulate phase using a Lagrangian frame of reference. So, for example, in the urban environment, whether it's wastewater or stormwater, we build treatment devices. Here I'm showing an example of a primary clarifier. In cities like San Francisco, land is at a premium. So you ask the question, how can I take an existing footprint device, retrofit it, and improve the performance? We typically do this with computational fluid dynamics. Here I'm showing an example of a primary clarifier where the performance is roughly around a 50% removal. Adding 3 baffles to that, the results are significantly improved. If we go all the way up to 17 baffles and make this like a chlorine contact chamber, now I'm up to a greater than 80% removal efficiency and a volumetric efficiency that is quite high. Now, modeling without measurement is hydrofantasy. So we back up everything we do in terms of modeling with physical models and measurements. And the agreement is excellent. Now, this is all great, but the problem is in urban environments, if we don't maintain our systems, they will fail. Maintenance is the Achilles heel of urban water systems. If you don't maintain your systems, you're going to get leaching from the particulate matter in the case of lead. In the case of zinc, this is true for every single metal. And unfortunately, our urban treatment systems might be effective at removing fine particles, but they are very ineffective for removing fine particulate matter, which is the more bioavailable and lethal particulate matter for aquatic organisms. So here's an example. We can remove big particles, but in a hydrodynamic separator, removal of small particles is meaningless. In addition, if you don't maintain these systems, their performance rapidly decreases in terms of months. So, to look at maintenance, we looked at maintenance practices across Florida. We looked at pavement cleaning systems, catch basins, and these things called best management practices. And the state asked us to create yardsticks and probability distributions to look at the mass of phosphorus and the mass of nitrogen per mass of particulate matter recovered, because they are giving the municipalities now credit for the median of these probability distributions as long as they document the recovery. We also look at inside and outside of wastewater reclaimed areas, because wastewater is now enriching the urban surface. And the primary method to do this is through street sweeping practices that are a function of sweeping interval, sweeping efficiency, and you can see that, in fact, we can recover a significant amount of particulate matter from these practices. Typically, street sweeping costs are about $30 per mile in the state of Florida, and we can equate that to dollars per pound of total phosphorus or dollars per pound of total nitrogen. So to sum up these results, if you look at different treatment or maintenance practices, best management practice treatment trains, if you want to pick up a pound of total phosphorus, it's going to cost you about $32,000 per pound of total phosphorus. If I go to total nitrogen, if I use hydrodynamic, screened hydrodynamic separator, I'm looking at $3,700 per pound. Compare those to maintenance practices. Maybe not as exciting, but they are far more economical. For example, street sweeping cost for nitrogen, not $3,700 per pound, but $165, and total phosphorus down at $257 compared to $32,000. In fact, this program has been so successful that most of the cities in Florida have adopted maintenance practices, quantifiable maintenance practices, and now are getting credits in their basin management action plans. So to conclude, urban water unit operations without hydrologic restoration, source control, and frequent maintenance aren't sustainable, period. Results demonstrate that sustainability practices such as pavement cleaning are much more economical. For urban water unit operations subject to wet and dry weather flows, widespread utilization of continuous simulation tools and computational fluid dynamics with monitoring is required. And so now, just to reiterate, municipalities across the state of Florida are now given pollutant load credits by the state of Florida for recovery of PM and associated chemicals in the built environment, resulting in remuneration of literally hundreds of thousands of US dollars to each municipality who utilize and quantify such recovery. If I have time, I'm happy to entertain a question.